Alright, good morning. Today we're going to open up a new chapter entitled Chapter 5. And the formal title of it in the text is Exponents and, actually the book's formal title is Exponents, Polynomials, and Polynomial Functions. I would have probably just called it Exponents and Polynomials. In particular, section 5.1, which we will start with today, is entitled Exponents. Alright, I'm going to break this up into two parts. As we've told you, part 1 is going to be today, online, and we're going to talk about rules for exponents and review those and apply those in several examples today. And part 2 we'll talk about next time. We'll deal with negative exponents. Again, this section in our text may be a little too long, so we're going to reserve part 2, negative exponents, for our next class. Alright, so on to the task at hand here. Rules for exponents, exponents part 1. Well, of course, I'm going to assume from your first algebra class that you know what exponents are and how to apply these simple examples. Well, in other words, I'm not going to tackle this from first principles. Well, we should all know that when we multiply the same bases to perhaps different exponents, we keep the same base and add the exponents. That's the first of 4 or 5 exponent rules that we're going to talk about today. And a simple example of this rule is, well, let's look at x cubed times x squared. Well, of course, I know x cubed is simply 3 factors of x, x times x times x. And x squared is similarly a product of 2 factors of x, and I think we can all see that I get 5 factors of x in the final analysis, and I could have gone just from here to here by adding these two exponents, 3 and 2. So let me rewrite that. X cubed times x squared, a little less ink in this version. It's equivalent to x to the 3 plus 2 power. And with that simple arithmetic at the exponent level, I can grind out a pretty simple answer. Similarly, x to the 11th times x to the 5th. Well, I'm not going to draw out 11 x's here and multiply them by 5 factors of x. I'm going to just claim that this is x to the 11 plus 5th power, and that's x to the 16th power. Let's do something a little complicated. A squared times b cubed times a cubed times b squared. Well, of course, we know that multiplication is commutative. Multiplication is also associative. That means I can rearrange products of factors any way I like. I would probably crunch the factors of a together as x squared times a squared times a cubed times, in turn, b cubed times b squared. And of course, I would just add these exponents. 2 plus 3 is 5, so this is equivalent to a to the 5th power times, well, b cubed times b squared is, of course, b to the 5th power also. And I think our author would write this answer most concisely as a to the 5th, b to the 5th, which of course implies a to the 5th times b to the 5th. One more simple example of this first rule, minus 8x to the 14th times x to the 15th. Well, of course, I'm not going to draw out 14 factors of x times 15 factors of x. I'll apply my rule. This is equivalent to x to the 14th plus 15th at the exponent level. And of course, if I add those two exponents, I get minus 8 times x to the 29th power. Notice that outside coefficient of minus 8 is not affected by the exponent sum. Alright, on to our next rule for exponents. Now, the book calls this product of a power. If I've got x to some power raised to some other power, or I should call this power of a power, not product, power of a power. Okay. Well, hopefully we all know that this is equivalent to x to the mnth power. In other words, I successively raise a variable to two different powers. It's equivalent to multiplying the exponents and applying on that base. For example, 3 squared cubed. Well, I suppose I could write this in longhand fashion, but I'll apply this simple rule and say, well, 3 squared cubed is equivalent to 3 squared, 3 to the second power times third power, and 2 times 3 at the exponent level is 6, not 5, 6, right? And 3 to the sixth power is 729. So I can easily evaluate that expression with this somewhat simple rule. Similarly, dealing with variable bases, to two different exponents, x to the 11th power, in turn raised to the 5th power, is x to the 11th times 5th power, a simple arithmetic power problem at the exponent level, really, and that's x to the 55th power completely simplified. Let's try another one. X squared times x cubed as my base and 6 as an outer exponent. Alright, what I'm really going to do is simplify as much as I can within the parentheses. Of course, I can crunch those base powers of x together. X squared times x cubed is x to the 5th inside the parentheses. And of course then x to the 5th to the 6th power is going to be x to the 5 times 6th power, which of course simplifies finally to x to the 30th power. Let's try a little harder one here. X squared to the 4th power times x cubed to the 2nd power. Alright, well, of course, this is an applied multiplication, and I do these exponent operations before I perform the multiplication. Well, x squared to the 4th power is going to be x to the 8th power multiplying these two exponents. 2 times 4 is 8. Similarly, I'll multiply these two exponents. Power of a power, you multiply the exponents. X cubed squared is x to the 6th power, and x to the 8th times x to the 6th is x to the 14th power, adding those exponents. Okay? So that really invokes our first two rules in one simple example, and you'll see a lot of that going on in the next few days or weeks to come. Let's look at another rule. xy to the mth power. Here I've got a product raised to a power, and the simple rule tells me I can distribute an exponent over a base product. xy to the mth is equivalent to x to the mth times y to the mth power, our third rule today. Examples of this: x squared y to the 3rd power. Again, applying this rule, I can distribute my outer exponent 3 on both factors of that base product. It's x squared cubed times y cubed, is it not? And of course, from rule 2, the second rule we had today, x squared cubed is x to the 6th power times y cubed is just y to the 3rd power. And I think our author would write our final answer in this concise form: x to the 6th, y cubed. Try another one here. Let's say I've got 2 y to the 4th power in a base, in turn raised to the 5th power. Well, the rule says if you've got a product to a power, I can distribute that exponent over all factors of that product base. What I'm going to do here is apply that 5th power individually on 2 and y to the 4th power, and then multiply the result. Well, let me write that out. This is equivalent to 2 to the 5th times y to the 4th to the 5th. 2 to the 5th power is, of course, 32. There should be a 5 here. 2 to the 5th is 32 times, well, y to the 4th to the 5th, power of a power. I multiply the exponents. I would call that 32 y to the 20th power as a final answer. Alright, if I can play this game with products, you might guess I can play it with quotients, and of course we can. Let me show you what I mean. Fresh screen, please. here we go. Let's say I've got a quotient raised to a power. Well, some may call a quotient really as a product of reciprocals, really. I can distribute an exponent over a quotient just like I can over a product. So this suggests a rule, a fourth rule today. Simple examples of this rule in action: if I've got x over y squared to the fourth power, well, by this rule, it says if I've got factors of a quotient raised to a power, I can distribute each factor of that quotient to that same exponent power. So what I'm going to do here is raise x to the fourth power and raise the denominator y squared to the fourth power and just divide the result. X to the fourth power, well, in my numerator that's just x to the fourth power. How about y squared to the fourth power? Well, I don't insist that you write every single possible step on these problems. After you practice a few of these, we should be comfortable with skipping some steps. In any case, I can simplify this final answer as x to the fourth over y to the eighth power. Let's do something a little nastier. Here I've got a fairly complicated quotient, minus 6x cubed over 5y to the fourth. If I want to raise that to an outer exponent, say raise it to the second power, I can grind this out really using my previous two rules in combination. Whether it's a quotient or a product, if I can raise a product or quotient to a power, I should be able to distribute my exponent over all factors of that quotient or product. So really I'm going to distribute this outer exponent 4 times over this product slash quotient. We go back to yellow here. Well, minus 6 squared, don't forget to square minus 6, times 8 cubed squared will result in my numerator. In my denominator, well, 5 squared is 5 squared, I'll simplify in a minute, times downstairs y to the fourth squared, power to a power, I multiply the exponents. Of course, I can simplify this a little more. Minus 6 squared is positive 36. X cubed squared is x to the 6th, not 5th, x to the 6th power. Downstairs, 5 squared is, of course, 25. And y to the 8th, well, it can't simplify that any further. It's just y to the 8th. So here would be my completely simplified response to this example: 36x to the 6th over 25 y to the 8th. Alright, so we've talked about 4 rules for exponents thus far today. Let's talk about a 5th rule. The book calls this our zero exponent rule. Well, all this says is x to the 0 power is 1. That means any base, no matter how simple, no matter how complicated, raised to the 0th power equals 1. We will formally prove this to you next time when we start talking about negative exponents. But for now, we'll take it on faith. Let me write some examples down. Let's say I raise any number. 5 is good enough. Raise any number to the 0th power, I will always get a 1. Similarly, if I take some complicated expression and raise it to the 0 power, it's 1. If I write something like this, 5 times x to the 0th power, well, remember we deal with exponents first, then products, so I would call this 5 times 1. X to the 0th power is 1, and 5 times 1 is, of course, 5. Final answer for that response. Let's try minus 5cd to the 0th power. Well, anything to the 0 power is 1. This negative sign is not affected by this exponent. The exponent doesn't see that negative sign, so I'd call this negative 1, and negative 1 would be my proper response there. How about something like this? 5a to the 0, b squared c cubed. Well, anything to the 0 power is 1, and the factor of 1 is redundant, so I would say this is equivalent to 5b squared c cubed. Alright, so a 5th rule for today: anything to the 0 power is 1. Alright, now let's see, one more rule for today, quotient rule. Well, all this says, if you're dividing same base expressions, for example, x to the mth power over x to the nth power, all I really need to do is keep that same base and subtract the exponents. So this is my quotient rule. Our book calls this a quotient rule. Well, let's see. Example, if I've got a to the fifth power over a cubed. Well, a simple application of this formula tells me this is a to the fifth, a to the 5 minus 3 power. And of course, 5 minus 3 is a squared. Oh, I'm thinking most of us wouldn't be so formal here for something this simple. 5 factors of a in the numerator, 3 factors of a in the denominator. We can clearly see that 3 factors of a in the denominator will cancel out with all but 2 factors of a in the numerator, and I'll get a times a, which is a squared in the numerator, over 1 in my denominator, and of course a divisor of 1 is redundant, so I would finally say this is a squared. So I can either formally apply the rule and get the answer of a squared, or I can maybe a little more informally look at things and get the same answer. It depends on how you want to attack any problem of interest. Should be able to work it out both ways, I suppose. Another example of that quotient rule, b to the 14th power over b to the 8th power. Well, again, our quotient rule says I'm not going to draw out 14 factors of b. I'm just going to apply the rule. B to the 14th power over b to the 8th power results in equivalent b to the 14 minus 8th power, and of course that's b to the 6th power. Let's try something a little more difficult. X squared y over 7xy to the 4th. Well, how am I going to grind this out? Well, I think we can see x squared over x, well, reduces to one factor of x in the numerator. If you don't see it, well, x squared over x, anytime you see a factor of x, there's really an invisible exponent of 1, and x squared over x to the first power, well, by the formal rule, it's x to the 2 minus 1, which is just x to the 1th power, which is just x. One factor of x will remain in my numerator. I call that a residue factor of x will be remaining in the numerator. Similarly, y over y to the 4th power. Well, let me do a little side work here. Y over y to the 4th power, I think you can see one factor of y in the numerator and 4 factors of y in the denominator. That's y to the 4th power is 4 factors of y. One factor of y in the numerator cancels out one factor of y in the denominator, and I will have a y to the cubed factor downstairs, and 7. Don't forget about the 7 here. 7 doesn't cancel with anything, so my final answer would be x over 7y cubed. Final answer there. All right, let me peek at the book. I want to look at number 40 in our book. Let's see. All right, number 40 in our book is, maybe it's too easy, c over d to the 9th to the 4th power. Let's try it. C over d to the 9th to the 4th power. Let me scroll down here. This is number 40 in our homework list. C over d to the 9th to the 4th power. Alright, my goal is to simplify these as much as possible. C is c to the first power. Right? One factor of c is really a c with an invisible exponent of 1. Well, c to the first power to the 4th power would be a c to the 4th power in my numerator. Similarly, I'm going to apply this exponent independently on the denominator. That's d to the 9th to the 4th power. So as a final result, I'd say I have c to the 4th power over d to the 36th power, right? 9 times 4 is 36. I also want to do number 42. in our homework list. Let me see if I can get there from the book. Let's see, 42 here is going to be 5t to the 8th over 3m cubed cubed. 5t to the 8th over 3m cubed cubed. Let me go back. 5t to the 8th over 3m cubed cubed. 5t to the 8th over 3m cubed cubed. Alright, now this one's a little nastier. Clearly I can see I have 4 factors in this base, which is really made up of quotients and products. Now, really the rule says I can distribute an exponent over a product and quotient, so really I'm going to apply each of the 4 factors in that base expression to the third power independently. 5 cubed, well that's 5 times 5 times 5, that's 125. T to the 8th cubed, well, power of a power, I multiply the exponents, right? Similarly, downstairs, 3 to the third power, well 3 to the third power is 27, and downstairs here, m cubed cubed, well, power of a power, you multiply the exponents. Alright, so my final response, 125 t to the 24th over 27 m to the 9th. Let's see, one more I want to look at. We'll call it a day. Let's see. 78. Let's look at 78. A to the 11th, b to the 7th over 100, a to the 15th, b. You write that down. Can't really show 2 screens at once here. So a to the 11th, b to the 7th over 100, a to the 15th times b and the denominator. Alright, let me go back to my tablet screen. Alright, so I claim I want to simplify this. Again, this was number 76, or was it number 78 in our textbook. A to the 11th, b to the 7th over 100, a to the 15th times b. Well, I think you get the idea. I can crunch these powers of a together and get a single residue expression for a in my denominator. Similarly, I've got powers of b here, which I can crunch together as one expression of b. Right, the 100 doesn't cross-cancel with anything, so I'll leave a factor of 100 or a coefficient of 100 in my denominator. A to the 11th over a to the 15th. Well, I think we can see that that factor of a to the 11th in my denominator cancels out all but 4 factors of a in the denominator. Somewhat similarly, b to the 7th power over b to the 1st power. Remember, if you see one factor of b, there's an invisible exponent of 1. Well, that will leave me with 6 factors of b in my numerator, and this would be my final response. B to the 6th over 100, a to the 4th. Alright, we're approaching 25-minute mark, so we'll call it a day. This ends part 1. Next time, negative exponents. And of course, I'm going to call that section 5.1, part 2. That's my designation, not the author's, okay? Alright, this concludes section 5.1, part 1, exponents.